Now, at this point, I want you to remember this volume that we did a couple of days ago, okay? And if you have where you drew this diagram, you may like to refer to it, but we're going to draw it again as well. So for now, though, let's just have our minds fully engaged rather than concentrating on the drawing of this. You can see, you might remember, let me just zoom in on this part for you. Excuse me. You can see what we're talking about here with cutting and getting slices, in this case annular slices, because you're perpendicular to the axis of rotation, okay? But if I took that same volume, right, and said, well, what if I don't want to cut that way? What if I don't want to cut perpendicular to the axis of rotation? The kind of opposite way, the alternative would be, rather than perpendicular, I can cut, here's the axis of rotation, I can cut parallel to the axis of rotation, okay? So rather than off this way, I'm going to cut this way. Now, every volume is an area that's been rotated, agreed? So here we've been getting these horizontal rectangles. Well, if I cut rather than perpendicular but parallel, I'm going to get vertical rectangles here, right? So let's think about this. If I go through here, let's pick a point like, let's go about here. It's pretty bad, but you get the idea. Come on. Okay. So I've just taken a vertical slice out of this. It's vertical because my axis of rotation in this case is vertical. Okay. I'm going to make it a little bit wide because it is supposed to be a. Well, actually, I should ask you. It's a delta something, right? I'm not going to zoom back out because then I'm going to muck up where my position is. But over here, you can just see a little bit. That's going to be a delta y. Do you agree? Right? So here, I'm going to have a delta x. Okay. But remember, I am still rotating this way. I'm still rotating this way. So when I take this guy and I rotate this way, what kind of shape do I create? Well, here's what I'm going to do. I want you to imagine I didn't have this whole yellow thing, right? Take away all the other stuff, just focus on this black part, right? Well, this part is going to rotate across and become kind of like this. This part at the top is going to do exactly the same thing. It's going to rotate around. There's going to be a part of it that I don't see in the back, right? And then over here, I've kind of got the opposite part of it, right? Now don't forget, this is just a slice. It's a vertical slice, right? So therefore this thing is actually hollow, right? This is like the inside, okay? So we have a name for this. We have a name for this. We've already said, if you take this kind of shape and imagine it as infinitesimally thin, we call this an annular slice. But this is not a slice at all. It's not flat in any way, okay? What you have instead is what we call a cylindrical shell, okay? So you can see the cylindrical shape, but it's hollow, right? It has to be hollow because you're rotating something that is infinitesimally thin, okay? Does that make sense? Now, here's the wonderful thing about this. Annular slices, right? Annular slices, we know what the area of an annular slice is, the cross-section, and therefore you just multiply by your delta x or your delta y or whatever, and you get the volume, okay? This thing looks like it's going to be, well, of similar complexity in terms of working out the volume of this thing, except it's not. It's way, way simpler. If you just are willing to do a bit of deconstruction, right? So if I take this shape, right, and I just cut it along the axis, right, then what you end up with is a marvelously simple shape. This is just a rectangle, right? Just a rectangle. I already know what the width of it is, or the thickness, I should say. It's delta whatever, in this case, delta x, okay? So all I need for the volume of this thing, or rather the area of the cross-section is, I need to know how tall it is, and then I need to know how wide it is. It's just a rectangle, right? Now, in order to work out, well, okay, where are these things coming from? On mine, right, I know how tall it is, but how do I work out this width? And the answer is you just have to remember back to where the shape came from, right? The shape came from a cylinder, which is just... It's just a circle, isn't it? It's just a circle, right? So therefore, let's think about this. You remember we said, here we go. We said, you can take this thing, you can muck about with it, you can make it anything you like. Let's think about what this is going to be. This is a volume, again, just like you told me before, right? The width of this thing is a delta x, right? Because it's a little width. I should say that little width is horizontally oriented. Okay. I'm going to add up. Now, just for this particular one, where am I going? Where is the smallest of these cylindrical shells? That's what this thing is called. And the answer is it's down here. There's this tiny little cylindrical shell with no volume. Yes? So x equals 0 is where I'm going to begin. Where do I end? Where's the biggest cylindrical shell? Is that way? Now I should say, this x and this x, I'm actually taking a bit of a shortcut. What they really are, maybe I should have written this, sorry guys, is actually a radius, right? It's the radius of a cylindrical shell that's getting bigger and bigger and bigger, okay? Yeah. Now, what's happening in here? Well, I just need to know the volume of this thing, which comes from the area of this thing. Do you agree? Okay. Now, you told me there was the edge here, which comes from the circumference of the top, which is just 2 pi r, and that's the circumference, right? And then what was the other thing I needed?
Delta. The height.
I need the height.
Height, yeah.
And then I need the delta x, right? Which is actually a radius. The radius is what's changing. Okay? Right. Now, this is really good. This is really, really good. I want to tidy this up a little bit because, in fact, in our case, delta r is changing horizontally. So it is, in fact, a delta x. That's why I kept on writing and then rubbing out. So I can now replace, in a similar way to how we did it yesterday, right? Sometimes your deltas, delta x, delta y, delta r, delta h, whatever, are equivalent to each other. So I'm changing everything in terms of x's because it's convenient to me. Yes, it would be. Yes, it would be.
So okay. In that case, when you change the top one, the sigma, under the sigma, wouldn't that be r equals 0 then?
Okay. Remember, I can choose whatever boundaries I like. I was going to choose x boundaries all the time because I'm looking at, like, I'm integrating over this interval. And I don't have, like as in this thing here, I don't know what r is. It's variable, but I don't know what it is yet, right? So therefore, it sort of doesn't matter yet which one it's going to be. This, as opposed to when we were first meeting integration by substitution, here we have to be a little more comfortable with having things where the integrals are mixed, the variables are mixed, and we have to sort of resolve, we have to go through steps to try and get it all in terms of one variable. Okay, now, just pause for a moment. What have we just established? Now we're going to work out this volume. We actually already know this volume though, right? We calculated this like a couple of days ago. Why might it be better, and this is the heading in case you wanted it, why might it be better to think about this as a cylindrical shell rather than, oh, where'd it go? Where's my annular slice gone? It's done disappearing now.
You mean the pineapple?
The yellow one, where did it disappear? No, seriously, where is it? It's gone. Well, it is infinitesimally thin, so I shouldn't be surprised. Okay, is it any better? What would lead me to think cylindrical slices rather than annular slices? What might lead me to think that? There's something on the board that tells me.
There's a y square.
Yeah.
So that you don't have to convert everything into y's. So
Okay, yeah.
With x's.
Very good. So the first thing is, I don't have to, do you remember when we were actually doing this volume, we had to do some serious twists and turns. You had to do a lot of like, oh look, there's this branch, and then there's this branch, and it's just like your head started to hurt, right? So that's the first thing. There's another simple thing, right? Which is that, look at this. Just compare this with having an r squared minus r squared, right? Just by virtue of squaring, you make whatever you had there, it's going to be icky, right? And we even had square roots, even after squaring, okay? So it's going to be like, yeah, I'm going to have some messy algebra. Whereas here, look at these. These are so nice and simple, right? And it's going to be even simpler once you recognize what h is. What is h? It's just the vertical coordinate, right? It's just y. And y is how, I believe this was, help me remember, I think it was 4x squared minus x to the 4, I think. So look, it's just a polynomial. And that's just a polynomial. This is super, super easy to integrate.